Hello, everybody. Today, I want to go through a relatively recent paper that was published. It's a fascinating paper. It has to do with internal architecture of the Great Pyramid, and it's a complicated paper. The hardest part about this is to go through the technology that was used to make the measurement, and so I want to try to make some sense of it. I'm certainly not an expert in radar technology. Um, I do have some skills reading scientific papers, so I'm going to show you how to approach a paper like that, especially complicated paper like this. And I think at the end of this, we will be able to make a lot more sense of it than without having some guidance. So it's informal presentation, so I'm kind of improvising it. I prepared a little bit for the talk, but I'm just going to go through the paper and extract the main principles as far as I understand them. So it's possible that I'm going to make a few errors, and I apologize in advance if that happens. I'm sure there's tech-savvy people out there that are going to call out some of the mistakes, and by all means, you can put those in the comment section if you like. I'm coming at this mostly from the Egyptology side. The main question being is what they're measuring real, or is it potentially an artifact of the measurement? It's a serious paper, so I think it deserves a careful review. Anyways, I put this up here, the Google Earth view, because I want to demonstrate something right up front so you see how this measurement was made. It turns out that the researchers never went to Egypt. What they did is they used a view from approximately 400 miles above the ground level. So I'm going to see if I can imitate that. So it's approximately from this height. What you're looking at is, of course, the delta of the Nile. This is Egypt, of course, and the pyramids are down here. I'm going to zoom in just a moment. But just so you get an idea, so this is the world map. This is Africa. This is Europe. Here's the Arabian Peninsula. And here is the delta of the Nile. And so if you zoom in about to this level, so about something like this, it's a little bit less, but this is roughly the height from which these measurements were made, which is of course incredible. So let me now zoom in further so you see what they were measuring. And they were measuring the Giza pyramids. Actually, there's some measurements that include the whole plateau, but the main purpose of the study is to see what's inside of this structure, which is the Great Pyramid. Here's the paper. This was published in a journal called Remote Sensing. It was accepted and published on October 19. So this is just about 3 weeks ago. I don't think this paper has received a lot of attention yet. I'm not sure why that is, because it's a big paper. I think there may have been a preprint that was published. It received some reviews, and then they had to address those. And then after those reviews were addressed, the paper got accepted in October, and then it was published a week later. There are some problems with this paper on the non-technical side. For example, I'm pretty sure this is an English translation of an Italian original, and the translation is not bad, but in some key areas, the language fails, in my opinion, the accuracy of that's needed to really well explain what they did, how they did it. So I think the translator did okay. I wouldn't say it's bad, but for a paper like this, I think you would need a even better translation. The other thing is there's also some just purely editorial problems, which I will point out some the kind of clumsy mistakes that were made. I'll show that to you later. And the third problem has to do with the content regarding Egyptology. So there's a few statements and comments that they're making, which I'm not going to dwell too much on it because it's not that important for understanding the main takeaway. But there's some statements that are factually incorrect that have to do with the Great Pyramid, with some of the Egyptology, and the conclusions is fine. At the end, they have their model which they present. They want to explain the new findings in the way that they see it, and that's okay. I'm actually not going to tell you what I think all of this means because I'm not sure yet. I'm just going to present the data as they are, and then you can all take you can take away your own ideas and design your own models. It's fascinating. If it's true, it's probably the most important discovery since Rudolf Gantenbrink surveyed the shafts from the king and queen chambers. It's a significant paper. I think this is even more significant than the muon scanning paper if it's real. But so that's something that we have to go through. I don't think we will be able to decide that based on my review, but this is just a warmer upper, basically, just to wrap your arms around what was actually done here. So, all right, so let me close Google Earth, and we're gonna go. I prepared a few slides. I have the paper here. There's a couple of websites which I will link in the description under the YouTube video. There's 3 different sites that are kind of helpful for the discussion. And then I have a few slides made. So let me go to the slides real quick. So this is just an overview, so you know what the paper is all about. And then I'm going to go to the paper with you and then show the slides again. So there's going to be some repetition just so it sinks in. So they show here the target of their study. So this is the Giza Plateau. These are the 3 pyramids, the Great Pyramid, usually attributed to Khufu. This is Khafre's Pyramid, Menkora. The direction here is north, and this is east on the right side. Here's a slice through the meridian of the Great Pyramid, showing the internal architecture, which is a little bit complex, but there are basically 3 chambers as far as we knew: subterranean, queen, and king chamber. The king chamber has a granite structure above it, which is usually called the tower. Here's the grand gallery. Here's the corridor that leads to the queen chamber. Here's the ascending passage, descending passage. Here's the entry, and here's the entry created by Al-Mamun when he broke either in or out of the Great Pyramid. Here's the shafts coming from the 2 chambers, the upper and the lower chamber. And then to the right is the more fine structure from the granite tower. So this will become important later when we look at the data. Now, in terms of satellites, just a brief review from just a little bit. I had to freshen up a little bit on it, but the satellite that there's many satellites that encircle Earth. This particular one is following an polar orbit. So this is what I wanted to show you. So this satellite is basically revolving around Earth near the North and South Pole. So this is called a polar orbit. And what the satellite does in this particular case, it sends radar signals down to the Earth. There's different modes. The particular mode that this particular experiment involved was to focus on a specific spot and then send basically radar pulses and then receive the response, the echo, so to speak. Echo is a term that has to do with acoustics, with sound, but it is analogous to echo when you talk about radar. So I'm going to use it because echo is something that many people are familiar with. So this is basically the echo that's coming back, and that echo is being read as the satellite sweeps past the target. So this is the particular satellite that the Italian Space Agency sent up into the sky a few years ago. Here's the geometry of this type of technology. So what they're and you don't have to focus on this at all. It's just the main lingo that's important here is the range, which is basically the distance on the ground between the satellite and the target. And then there's also what's called the azimuth direction. So it's a two-dimensional data acquisition. So you're sending pulses down to the target, and then you get an echo back while the satellite is moving. And depending on what that echo looks like in all these different at all these different times, you get resolution in terms of this point that you're studying. This is not that important for the presentation, but for completion, I just wanted to show you. So the data were acquired at 650 kilometers, which is about 400 miles. The satellite is moving at 7 kilometers per second. So it takes just about 100 minutes for the satellite to go around Earth one time. The measurements are very quickly done. 15 seconds is one measurement, and then the satellite is gone. It takes 100 minutes before it sweeps back down. But then since Earth rotates, let me just go back, right? So the satellite sweeps down or sweeps up depending on which way the satellite is moving, but the Earth is also rotating, right? So if the satellite happens to come down or go up at the same time when the Giza pyramids are in the orbital plane, then you're going to have an encounter, right? Then then the Earth rotates, and then the next time the satellite sweeps around, it's not going to see the Giza pyramids, but it's going to see something that's a little bit west of the Giza pyramids, and on and on and on until it happens again, right? So when you do a data acquisition, you have 15 seconds, you do the data, and then you can do another data acquisition in another time in the future. And so it turns out it takes about 2 weeks to be able to do this, to repeat the data. So now there's a couple of terms. They're not that important, I think, but just I'm just going to tell you what just from my reading. So a chirp is basically a way to increase the resolution along the azimuth. Okay, it's basically you're sending a whole set of different frequencies, which is why this is called the bandwidth. So the width of these different, from the highest to the lowest, is 400 megahertz. So you basically, it's kind of what whales do under the sea when they send an echo out. It's different frequencies. Why? Because some frequencies are not going to come back or not give you such a good signal, but there are some frequencies that are going to give you an excellent response, an excellent echo that you can use to locate the target. And so that's why you send a whole bunch of frequencies out there in the hopes that, one frequency or a few of them will give you a good signal. And then, so the Doppler is basically a way to detect movement. So let's say you have a target that's fixed versus a target that's moving, then the Doppler will be able to help to detect that movement. The antenna length on the satellite is 6 meters, so that matters in terms of how well you can resolve the images. But remember that the satellite is also moving, so the type of data acquisition here is called synthetic aperture radar, which means that the satellite is creating, sort of by its movement, by its movement across the area, it's creating a gigantic antenna, and you can use that in order to enhance your resolution. There's this, what I was talking about, spotlight. So there's different acquisition modes of the satellite. Here they are, but the particular one that they were using is this one. So they basically focus on a specific area instead of scanning different areas. Okay, so it's called spotlight. Polarization means that this just helps you to identify the signal that's coming back. So you filter the electromagnetic waves through a polarizing filter, and it either will, in this case, there's only 2 directions, either it's vertical or horizontal. So just another way to increase the signal. And then we already talked about all of this. So here's, this is from the paper. they are showing once more the geometry of the data acquisition. Here's the satellite sweeping across the azimuth, and remember, azimuth is basically the orbit of the satellite going through, sweeping through, and the range is the distance between the satellite and the target on the ground, which is the Great Pyramid in this particular case. So they're showing proof of principle, basically. What are they looking for? They're looking for tiny movements of the Great Pyramid in all these different places, okay? So here's just the proof of principle. They're showing you that you can detect these vibrational displacements as a function of time. Here's along the range, which, remember, that's the distance, and then across the azimuth. So you can, in both dimensions, you can detect these tiny movements. There's a lot of math in the paper. These are some of the parameters that you use in order to develop the formulas, and the formulas are basically the mathematical description of what is being measured and why you can measure it. So here now is what they're actually went after. Okay, so what they're saying is that the Earth, because of seismic activity from the city of Cairo, people, millions of people driving cars, jumping up and down, all kinds of sounds, loud sounds, all of these things cause vibrations, and this all amounts to slight movements up and down of the Earth underneath. And of course, we have also wind that sweeps across the Cairo area that moves the pyramids, and then there's natural Earth vibrations, seismic waves that get created, and all of these together cause movements. But these movements are more exaggerated when there's resonance. So when there is a space where the movement can be amplified, then you're going to get a stronger signal. And that's really ultimately what this experiment is all about. By detecting these stronger movements, the researchers are interpreting those to represent spaces. So more on that, but this is just to explain. Basically, they're using the analogy of a weight that's suspended by a spring, and this weight is going up and down, and that's kind of the seismic motion, right? And so they can detect that when they fly across with the satellite using their technology. So once they collect the data, this is how they process the data. So you get a single SAR image. SAR is synthetic aperture radar. This SLC mode is this is just the way that this is kind of data they're receiving and how they're storing the data. This is not so important for understanding the paper. It's more important for the technologists, how they basically how they're how should I say, how they're storing the data, how they're capturing the data. They're capturing them in this mode. It's called single look complex, basically. So then what they do is to bring out the signal, they process these data through filters. Okay. Then in order to look into the interior, they select points along a line. I'm going to show you that in a moment. It's called tomographic. Tomographic means you basically slice a line through the pyramid, through the object, on the surface of it. First, you make a line across the surface, you measure all those points, then you check each pixel, each particular point is tracked from one instance to the next, and this is extremely important for what they're trying to do. And then you have to basically now reconstruct what's going on inside the Earth or inside the pyramid from the surface data, and that's called acoustic tomographic focusing. This is not that different in general terms. This is not that different from a CAT scan. When you do a CAT scan, the main difference is that X-rays go through the body. Obviously, the radar does not go through the Great Pyramid, but what they're doing is they're checking for slight vibrations on the surface, and from those vibrations they can reconstruct what's going on inside. In other words, what resonating point inside is causing the surface movement up and down or sideways. Okay, so this develops. I mean, this involves some calculation, and so this is probably the most important step. I couldn't find it in the paper how they did. That's one potential major oversight that they didn't publish this. This may be, of course, mentioned in another paper that they're referencing, so maybe they left it out. But in terms of the interpretation of what they're trying to do, I think this is almost the most important part of the data processing. So here's how they collected the data. They had 12 different flyovers, basically different parts of the phase of the orbit. And here's the different polarizations that they used, and they had basically six flyovers to do the external data and 6 for the internal data. This was all done between October 2021 and just this year in April. And the reason for that is because the satellite, the COSMO-SkyMed satellite, the second generation satellite, there's right now one, as far as I understand, out of 4 planned. And it was only launched in 2019. So this satellite was only up for 2 years. And it's a more powerful version of the prior version. So I have the 2 websites here if you're interested. I'm going to put the links. So this is COSMO-SkyMed. This is the original one. There's some things you can do on this website. I haven't checked this out, but it's interesting. So here's the different launch dates for the original set of 4. They have a certain shelf life. I think it's 5 years or something like that. This is the height. Some of the data you can get from here. And then this one is the second generation. So this is the first one that went up in 2019. The second one is up, but I'm not sure if it's functional yet or if it was ever functional. From my reading, this is not working at this time, but I could be wrong. So similar height, nominal local time at ascending node. So usually the nice thing about a polar orbit is that it's basically synchronized with the time of the day. So you can, since you're sweeping sort of with sunrises and sunsets, right? So you're synchronized to the day. The orbit is not exactly 90 degrees. It precesses a little bit. So what happens is you come back to the exact same configuration after 1 year. So it is synchronized to the orbit around the sun. So this is the orbit period, just a little bit less than 100 minutes, an hour and a half. And so every 16 days, you get to repeat the same place. And so you can repeat the experiment. So it's a little bit of a long waiting time, but as you can see, it's well worth it. Because of the data you might be able to get out of it. So so now let's talk about some of the results. So this is the first proof of principle. So it's called an interferometric SAR result. So what they basically did is they compare 2 images taken at 2 different times, and then you compare the data, and then you get the 2 sets of data. They interfere with each other, right? And that's how you get these interference lines. It tells you basically if there has been movement or not. So this is the first proof of principle. It's showing you if there is an interference pattern, that means there has been some movement. So it's the same, you're looking at basically the same pyramids on the same ground, right, at 2 different times, and you wouldn't expect there to be any movement, but unless there is movement, then you're going to see it. And as you can see, you can see it. So there is certainly movement, and the movement that they're saying that's causing this is this seismic seismic movement of the pyramids up and down and sideways. It's kind of a resonating pattern. And so now what they do is they look close up on these fringes, and what they find is, interestingly, which what we know, is that there's a concavity in the pyramid. So the concavity is more pronounced at the lower, closer to the base, than when you go up. But certainly most people that have seen the Great Pyramid have seen this. and it is a well-published, it's long known that the Great Pyramid has these indentations, and they are confirming that that with this technique you see this indentation. But the interesting thing is they're seeing it not just for the Great Pyramid, but also for the Khafre Pyramid and for the Menkora Pyramid. So here's this is the Khufu Pyramid, Great Pyramid. There you see the indentation, right? It gets less pronounced as you go up the pyramid. Then this is Khafre, again more pronounced at the base, going up. Now this image is proof. Again, they have to prove that what they're doing is working, so they compare it with LiDAR measurements, laser directed surface and subsurface measurements. And what they're saying is that their data agree well with the LiDAR scan. So they're, again, they have to demonstrate that what they're doing is valid, and LiDAR, of course, is already has shown great value. But what they're saying is that their data have a nice correlation with LiDAR. That's basically what this means. Now here's the major result that come out of this paper. They found 20 different structures that were unknown before. We're going to get into that. I'm just summarizing. This is the summary table that shows they have given a name. It's called a tag name, structure number, or they call it tag. Here's the description. We're going to get into that in a moment. Here's the 3D model. And of course, this is mind-boggling. Here you see in black, you see what was known. And then you have all these structures that they're seeing with their technology that nobody had any idea that they existed, except for what's in green. So this is the big void that was detected in 2017 by the Muon project. And they are confirming the existence of this structure, which is important because you have a second, basically completely different technology that is confirming it. Although the shape of this is, as you will see later, is not the same shape as what the Muon project people believe or how they interpreted it, but there may be an explanation, which I'll get into in a moment. So this is basically the run-through summary. So now I'm going to go through some of the details in case you want to read the paper. I've highlighted a few things. So how do you approach a complicated paper like this? So when you scroll through this paper, okay, there's a lot of text. There's a lot of abbreviations, and then there's a lot of words that are not familiar to many people that are not in this field. Okay, so if you're not an Egyptologist, if you're not a radar expert, if you're not a satellite expert, then you're gonna scratch your head and saying, "What the heck does all of this mean?" So this basically repels a lot of people from looking at something like this, and so you have to leave it to the experts to basically interpret the paper and tell you what it means. But I think it's important even that lay people can actually go through a paper like this and get something useful out of it. So and I just want to show you how you do that. So the abstract is always important because it gives you the bottom line, is what are they saying in this paper. This is the summary of it. And what they're saying is that the obtained results prove very promising as a high-resolution full 3D tomographic imaging of the pyramid's interior and subsurface was achieved. That's a tall claim. Looking at the data is justified for them to say it. The main question, again, is does the technology, in fact, measure this? Okay, so we're gonna get to that at the end. This is an even even more taller claim yet. It says becomes transparent when observed in the micro movement domain. So it's like basically they're saying we were able to take the walls away and visualize the entire interior. It's an incredible statement. I have to say they're not necessarily exaggerating looking at the result. So the abstract gives you the big picture. Now the introduction. So we're gonna go through the Egyptology. Let's see. This first section here, the Egyptology. I'm gonna let you read this and you know, there's a couple of things. It's not that important. I think you can discount it. There are some statements that are not completely accurate in here, but it's not that important. I think I'm just going to skip over it. So here's a brief review of what's been done before in order to visualize the interior architecture. You know, here's, for example, Houdon's theory that there's an internal ramp, microgravitometry studies they're citing. So they're basically doing the homework and saying, you know, we've looked at all the previous studies that try to investigate the interior architecture. You know, we've done our homework and we're making now a contribution. And so the particular contribution, here's the key sentences: another independent non-destructive method is needed to confirm this discovery. And by this discovery, they're talking about the muon project. They're mentioning the large void that was detected. Now, here comes the more important part. So, so this is really when it begins. They talk about their technology. Okay, so the technology is synthetic aperture radar. Now, the second thing I wanted to say is when you read a paper like this, you're going to see a lot of abbreviations and acronyms. And this has to do with the fact that when you write a paper like this and you're using long names, that it's just more efficient to abbreviate them. But for the reader, unless you know what this means, you're going to get lost very fast. So one thing you have to do is you just have to look up in the beginning. That's just a little bit of homework you have to do, is look up what all of these things mean. And they usually, the first time you use an abbreviation, they define it. So in the past, here it says, for example, synthetic aperture radar, and then they say SAR, but they use the SAR even before they define it here and here. So this is something that when you write the paper, you should do better than that. You should make sure that you define it the first time you use the word. And they may have done this earlier, but you know what I'm saying? This is an editing problem. The text was not edited well. There's also some composition problems, but anyways, I just want to get through this so you get the takeaway. Here's micromotion. So this is an important abbreviation, that key. So micromotion is basically these tiny movements of the pyramid. Different parts of the pyramid are moving at with different energies, and this is really what they're detecting with this synthetic aperture radar from the satellite. Okay, so these two abbreviations are probably the most important one. There's this SCL, so satellite signal look complex. This is just the way that the data are being collected. Okay, it's not that important for this paper, in my opinion. Multichromatic analysis. They're abbreviating this MCA. I think this has to do with the Doppler, what they're looking at in their Doppler analysis, but it's not that important right now. There's CHIRP. Okay. Here's the name of the satellite. Okay, so anyways, I'm just giving you, I'm just demonstrating to you that when you read a paper like this, even at this early stage, a lot of people may just fall off the cliff because they don't know what all of these abbreviations mean. So, but you can make it past this first section if you just look up these things, see how they're defining it. And even if you don't understand what it means, it helps if you look it up actually before you go on, because but you know, sometimes you skim through it first, then you look it up, and then the second pass, it gets better. Each time you read the paper, if you want to spend the time, it gets better. I can attest to that. So now what they're basically explaining here is how this synthetic aperture, how this is working. Okay, they're talking about Doppler, micro Doppler effects, etc., etc. I'm going to skip over this, and I'll just give you the bottom line in a few moments. So I showed this to you. This is how these are the specific specs for their data acquisition. Here's the Giza Plateau description. So they're doing all their upfront homework, basically. Here's the internal architecture. I mentioned this to you, and here's the method. So now, so what they're I'm going to use this slide here as a starting point. So what they're interested in, you have to imagine this pyramid here, just like everything around it, is moving very slightly, ever so slightly. And this has to do with above the ground and below the ground motions. And wherever you have a space, a hollow space, those movements could be amplified. Okay, so you're going to get a stronger signal. And let's say that space is right below the surface of this point. Okay, then if you have an amplifying void, a space inside of this pyramid that is amplifying, then that amplified movement is going to push its way all the way out to the surface where the circle is, right? So that is what you're detecting. You're detecting the surface motion of something that's going on deep inside. But let's say this point is right above a space deep inside, okay? But this point over here is not, okay? So you're going to get a stronger signal here than you're going to get here. That's really what they're measuring. They're measuring when you take a slice through the pyramid, you look at all the dots on that line and you check, and you do the same thing, let's say for here, here, and there. And when you do all these slices, right, and you look for these tiny movements, then what you can recreate from all of these samples, you can recreate a three-dimensional resonance signature. And that tells you what's going on inside of the Great Pyramid. So it's ingenious. What it helps them is there's the two major things. The first thing is the realization that these tiny movements are occurring. And the second thing is to have a technology to actually measure that. That's those two things coming together it's the key to understanding this paper. So here again, proof of principle. So what they're doing is they're picking this particular point, and they look at the signal that they obtain from this point, and it turns out that you see a vibratory signature, okay, so this is the magnitude of it, which it's significant. When you look at the scale, though, we're talking about 1 times 10 to the minus 10, 1 times 10 to the minus 7 meters. So it's tiny, right? These are tiny vibrations. It's not like, we're not talking about earthquakes here. We're talking about tiny resonance, and they're able to measure this. It's incredible from 650 kilometers above the ground. To me, it's just amazing what technology can do. But there you go. Apparently, you can see this. And then here's sweeping across with the satellite, so you can see it in both dimensions, in the range dimension and in the azimuth dimension, I think, right? No, this is the range. I'm sorry. This is the range, and this is the azimuth. So in both, you can see it across both dimensions. Now, these data go through a two-dimensional filter. So this is just, you have to imagine when you have all this noise, in order to be able to see the signal from the noise, you have to filter the data. And it's not that important for this paper. It's just that they obviously, any radar acquisition requires that, because you have to imagine, when you're sending out a signal, most of that signal doesn't come back, it doesn't echo back, only a small portion of it. And so, but you also gonna get bounce backs from all kinds of other areas that are being, where you have electromagnetic waves bouncing off from the sky, from other sources. So you get this whole you get a whole array of different electromagnetic waves bouncing back. And then what your job is basically now is to filter out the specific signal that from the pulse that you send out, right? You're sending out a pulse that bounces back. Some of that pulse bounces back, and you want to detect that little bounce back, that little echo from all the noise, from all the other radiations that coming back. So this is why you need a filter, but not so important. But just the fact that they are doing it. when you read the paper. So the math, it's with a lot of time, you could probably explain it, but they have to do this. They have to explain that what they're doing has a mathematical basis for it. It's intimidating, but it's not as complicated. You could figure it out. I'm not going to go to it today. It's not important, I think, for us. So anyways, now here, this is an important part of the paper because the Doppler sub-aperture model. So what they're doing here is to, the upshot of this is that these tiny movements create basically a two-dimensional, if you didn't do sub-apertures, if you just sweep across the area, and then you're going to get a smear because of that vibration. So, right, it's kind of, that's how I'm understanding it anyways. You're going to get a smear across the range and the azimuth. And what they did, they said, no, we want to know what are the individual components of the smear, because that is what we're looking for. We want to quantify the smear. And in order to do that, they use the Doppler sub-aperture model. And basically, this is how they are either. So this is the problem that I had. I don't know if this requires multiple passes with a satellite or if this is a data processing technique. I think it has to do with the way they're processing the data. So they're looking at slices. So basically you have the satellite flying by, looking at the same spot, right? And sending pulses, and then the echo comes back. Then what they do is they take that echo and they slice up the echo into low, medium, and high, let's say, frequency bands, because they want to see if they do that, if you see these if you can resolve these tiny motions of the tomographic line. Because if you can do that, then you can quantify it, and if you can quantify it, then you can reconstruct from that what's going on deep inside of the pyramid. So this is, I'm just giving you the summary of it because that's my understanding of it anyways. But that is an important part of their approach to this problem, the Doppler sub-aperture technology. And so chirp Doppler sub-aperture strategy. So this is the strategy that they were using. There's the talks of the filter. So all of this is basically explaining how they process the data in order to measure these tiny little displacements. Okay. So here is an important statement. It says it turns out, so a single point stationary target has a two-dimensional rectangular nature with total length proportional to range, azimuth, bandwidth. So the movement of a point target with velocity in both directions is immediately warned by the focusing process resulting. So normally the radar processing technology, they will try to smoothen out these smears, right? So if you have a local target, if you have a tiny little movement that smears the data, then the system, the processing signal, they get a warning, and they will see if they can correct that smear. But in this particular case, the researchers were actually interested in that smear. And so, because those movements is what they're measuring, right? So a single point stationary target has a two-dimensional rectangular nature with total length proportional to the range bandwidth. So I just wanted to show you, this is exactly a repetition of what's written up here. So they just spelled this. So this is clearly an editing problem. They should have, this is just a duplication from what I can see, slightly different, and somebody didn't edit this out. So it's a little sloppy. So this is my main problem with this paper, is that the English is not as good as it could be, the translator. I'm not blaming the authors. I'm just saying is whoever translated this paper should have been a little bit more careful. From the compositional point of view, I would say the authors they may have explained things a little bit better. They're not doing a bad job, but it's not, for a paper like this, they should have done a better job. Let me put it this way. And if they can, then they would have to just have an editor go through it and help them to express the to make it more accessible for a wider audience. And then the editor would have easily picked up on this stuff and, you know, just eliminated this, whichever version, you know, they don't want. Anyways, and then the third thing is that some of the factual information from the Egyptology is not correct. But moving along. So now here's another key statement. So the backscattered energy from moving targets is distributed over several range azimuth resolution cells. So you have to imagine when they take their data, it's a two-dimensional the data are along two dimensions, right? The range and the azimuth, and they're pixelated, right? So each individual point is a pixel, and their resolution is about a meter. So each meter represents a pixel, but the energy that's coming back, the backscattered energy is the echo from, if the target is moving, then that movement is basically smeared across more than one cell. And this is what they are fixing with their strategy. They are tracking each individual cell from moment to moment so that they can compare what that cell is doing across the measurement time, okay? Because it helps them to quantify these tiny movements. So you have to imagine that they're basically using a problem that other people have when they do radar analysis to their advantage by actually solving this issue with a new approach. And by doing that, they were able to measure these micro movements. Okay, so now, and then one more thing I have to explain. So the tomographic model. How did they translate these tiny movements into the interior architecture? So it says the vibrations present on the tomographic plane extend from the Earth's surface to a depth of a few kilometers is assessed. Okay, so they're basically, we already went through this, right? So you have to imagine you have each point is going up and down at its own pace, depending on how resonated it is. So some stronger, some less strong, some weaker. You get these different energy profiles. So this is time, this is energy. So if you have a wider, so here, for example, you see how these lines are wider, means more energy, means more resonance. So at this time, okay, you're measuring something that is resonating, and that reflects in their interpretation, it reflects a void, a space where you can have resonance develop. Okay, so let me see the vertical dimension of tomographic line. So here, the tomographic line of interest is constituted of the series of contiguous pixels laying on the green plane. So I'm going to show this to you in a moment. So a tomographic line is as if you take a knife, let's say, and cut the pyramid in a certain plane. Okay, all the points that lie on that cut is one tomographic line. If you do several cuts like that, different orientations, if you put all of those together, you can recreate a true three-dimensional image of the interior of the structure. So, all right, I think let's go to the data. So this is again how they process the data. Like I said, this is probably the most important aspect, acoustic tomographic focusing. So you're focusing this up and down movement, right? So you're checking the surface of it. So let me go back to this real quick. You're at the surface, right? You're checking these tiny movements, but those movements are a result of what goes on underneath, right? And so depending on how close the surface is to a resonance, let's say, you're going to get a stronger or a weaker signal. So see here, for example, this is way down, so you may get a weaker signal. But if this is higher up, then you're going to get a stronger signal. So from this signature from the signatures of these each individual pixel, you can reconstruct these particular areas where you have higher resonance. So this is my understanding of it. Unfortunately, they didn't explain this, and I think this is maybe the biggest shortcoming in this paper. But I don't want to blame them if it's not true. So I couldn't find it. That's all I'm trying to say. I could not. The details of this is not explained. They do explain the filter. They explain this. They explain that number 4. And then the pixel tracking, that is pretty straightforward. But this particular aspect, I'm not seeing it in the paper. Maybe it's hiding in the math. Okay, so let's go to the results. Yeah. So we already talked about, I'm going to skip over this because I already mentioned it. So they were basically able to show that all 3 Giza pyramids have concavities, which is interesting. Certainly, it's not easy to see it with, I mean, I haven't seen it on the Khafre pyramid. It's not, you can't see it with your bare eye. That's what I'm trying to say. With Menkaura's pyramid, you can sort of make it out, and it's been described. But on this one, it just goes to show it's more subtle, but it's there. So this is part of their proof of principle. But and then this has to do with the LiDAR. We already went through that, so I'm going to skip over this. These are the 20 structures they found. Here's the structure. So I think it's kind of, there's a lot of data. So before we go to the individual ones, I'm just going to review them real quick. So here's the entry. This is just an image of the chevrons on the surface of the Great Pyramid. Now, the structures in black is what we knew. Okay, everything else, and then the green number 19 is the big void. We knew about that. Everything else is completely new. And the most striking one is this wishbone shaped huge structure that apparently is inside of the core of the pyramid that no one knew about. And not only is this inside the pyramid, but it goes deep down into the ground below the Great Pyramid. Supposedly, my understanding is these are hollow spaces. So even though this looks solid, but I think it reflects hollowness. So these are actually corridors or large spaces. This is clearly non-random because there's symmetry to it. You have it on both sides. And when you see the data, it's very difficult to explain this away. I mean, the signal is there. It's a high signal to noise ratio from even just from a layman's perspective. But there's also the other confirmatory aspect of this is that they detect the big void, but they're also detecting a chamber in red here under the queen chamber, and they're detecting another chamber to the south, lower at a lower level to the south of the queen chamber, and then they're detecting all these trusses here that are coming from a square structure around the tower, around the roof of over the king chamber, and this square-shaped structure is connected to the big void with these 2 canals. And this whole thing is suspended almost, I mean, suspended, if you will, with these trusses that are connecting it to this sort of, it almost looks like a, if you think of it, looks like a steel frame of a building, and this, with cement all around it. And this is sort of the steel frame of it, if it were made from steel. That's kind of what it looks like. But it turns out that this is connected with these trusses. Who knows what they are? Are these corridors? Are they? There must be some spaces, because that's why it resonates. So they supposedly are hollow. That's my understanding, anyways. So this is just kind of a brief review, and now I want to show you some of the data actually. So here is one tomographic line. So it goes up and down across the half base, the side slope of the Great Pyramid. Now what they're doing here is they're saying, in order to demonstrate that the technique is working, we have to be able to show that we can detect the known structures. So this is the first part of this, and apparently they can. So here's the data from this tomographic line here. Here's the scan. The intensity, red means more intense, right? So this is supposedly the resonance that they're seeing. The seismic, the size, each pixel is quantified in terms of its seismic signature. So a red color means a stronger seismic signature. And then they zoom in. This is just a zoomed out look of it, but here they're detecting the tower, right? So if we zoom in, here's supposedly the tower, and there's another image where you see it much better. So this is basically, it has to do with the scaling, right? So if you make this red, then this area has to be blue, but this actually is more quantifiable. You see it in a moment. So here's the overlay towers, not so easy to see in this image. Here's the queen chamber. So they're saying that you can certainly see this, right? So there's the horizontal corridor that goes into the queen chamber. Then here, what they're seeing again is there's the grotto. Okay, now the grotto gives a very strong signal because it's a bigger hollow space. The grotto is underneath the horizontal. It's underneath the queen chamber and above the subterranean. Halfway, there's the grotto shaft. Okay, connects to the grand gallery. And here underneath the grotto, there's this big hollow. So it's interesting that that gives them a very strong signal. Now here, this is what I was talking about. So if you zoom in on the pixels and then you do the quantification, you get a much more clear signal. So and you see the resonating portion is, interestingly, it looks like it's corresponding to the granite itself, not necessarily the space. These spaces, the relieving chambers are these white spaces. The granite that forms the floor of these chambers is giving this strong signal here. And here's the different line. So this is now the Tomographic Eastern. So this is the eastern side of the Great Pyramid. Here, now they're looking at all the points that are lining up here. Okay, and when you do that, and then they're also looking at so if that's east, that's the north face, and as you can see, that's a vertical line, that's a horizontal line. So different views, different perspectives, and then you get different intensities, different resonance intensities. Here's another. This is now from the west side. So this is the east side. So west side is the opposite side. So here they scanned the upper portion of the west side. Here's the signal. And I mean, you can already see there's the signal is not difficult to find. I mean, there's clear linear streaks. This is not random signal. This is very significant distinction between the actual signal and the background. So the data are, in some instances, the data are unmistakable from my reading of it. Anyways, look at this one, for example. There's a clear line here that is inside. And this is part of the interior, right? So there's something that's straight running across when you scan it this way. Here is the bottom slice of the western side. So this was that's the eastern side, a little bit higher. That was the western side, a little bit higher, and here's the western side, a little bit lower. So they obviously wanted to slice the pyramid at different levels to check for the different structures. So here again, you have really clearly defined structures. And then what you do is when you have all these different samples taken, so here, this is from the northern side. So we have east, west, north, and then there's also a southern side. Here's western vertical. Here's eastern vertical. Here is here's north south. So this is the meridian, basically. So they basically did all 6 ways, right? So you have 1, 2, 3, 4, and they have vertical and horizontal, and then they have the meridian and the east-west axis. So multiple ways to slice up the pyramid, and then you put all these all of these points, all these different resonance signatures, you put this all together into a 3D map, and then you end up with this. So now what they're basically doing is they put this into a CAD program, computer assistant graphics, right? And then now they start labeling all these structures, right? So tag 4, tag 7, 1, etc., and that's how they come up with this, with all these structures. Different angles, because it's obviously it's crowded. They found 20 new structures. It's an amazing, absolutely amazing discovery if this is for real. And so in order to be able to view all of these things, they produce all these different angles. They rotated their model, and then they double check it versus their tomographic measurements. So for example, here tag 2, that's that big ramp. I'm just going to call it a ramp. It may not be a ramp, but it's basically, or it looks like a staircase, if you will. Whatever it is, it produces this very clear linear signal inside, and it has a strong resonance in certain parts of it. So they are representing this as a step structure. Here you can see, let me see if I can zoom in on this. See, there's the queen chamber. Here is a space under the queen chamber, and this has been described, this has been proposed by other researchers in the past that believe, and even Zaya Was himself in a lecture recently said that he believes there is something under the queen chamber. So there it is, they're confirming that prediction. But what they are also saying is that there's another chamber or another space further to the south over here. And if Hawass is correct and there is a mummy in here, then it's probably actually in here, because that's maybe the more likely one. I don't know if this is a canal. It looks like it's a canal that's going also underneath the Great Pyramid. So, but so it's difficult to look at all of this and say that this was all made to be a grave. I'm sure this is no longer the most likely explanation, if it ever was. This is so complicated that you can't help but wonder if this was made for an entirely different purpose. It doesn't mean that somebody couldn't be buried in here, but that's not maybe the entire function of why this was built. That's my initial impression. But I am open to new discoveries. So we'll see I'm sure a lot of people are going to come up with all kinds of models to explain this. Some of it may have to do with construction, some of it has to do with function, some of it may be ritual, but I think this is a game changer. This is basically opening up the discussion to to new models that we didn't think about, and some models that were thought about may actually be enhanced by this. Some other models will be weakened by these new findings. For example, I don't see an internal ramp here, a spiral ramp that goes all the way to the top. They certainly did not see that. And they do demonstrate, however, that they can find very fine structures. Certainly, their resolution is good enough that they should have seen a spiral ramp if it existed. So that is one of the main takeaways from this experiment, in my opinion, that it rules out the spiral ramp proposed by Jean-Pierre Houdin. It confirms the presence of the big void. However, it does not show the big void in the same shape as was the muon project people thought. So this is another major takeaway from this. And then, of course, the third major takeaway is that you have this gigantic structural, potentially structural or functional hallway system here. And then the fourth major takeaway is that you have at least you have at least 2 new chambers from the looks of it. The fourth takeaway are this system here, this in gray. So it's better, maybe you can see it better here. So there's this bar, this corridor that goes right across. And interestingly, I looked this up. Number 7 actually coincides with the hotspot on the thermography. So they did. This is the east face of the Great Pyramid. They did a few years ago. I think it was the Muon team that tested how the pyramid heats up in the morning, if there's any differential heating, and they found a hotspot in this location on the east face. And I looked at this yesterday to see how that relates to this location of number 7, and it turns out pretty much exactly where that hotspot is. So that's another interesting corroboration potentially. So the thermography predicted this particular structure, number 7. There's another view. Here's the different tags. So it's just fascinating that they're seeing these very distinct heat signatures, heat meaning resonance signatures. So I think that's pretty much it. There's a lot to study in there. I think the most important thing is for people with technological background to confirm that what they are measuring is indeed what they think they're measuring. I can tell you is, I don't know if I can find this in the introduction, it does mention that the technique was used on volcanoes. Let me see if I can find that real quick for you. That might be a useful reference to look up and to see if how well it performed in that context. So that reference is, let's see if I can find it for you real quick. If I can't find it right now, it's not that hard. You just look for it. Wait, just check for. Let me look it up for you real quick. You just type in volcano. Yeah, here it is. So it's on page. It is on page 5. So there's a reference. It says an imaging method based on the analysis of MMs, so micro motions present in volcanoes and generated by Earth underground seismic, is described in 64. So this actually, one of the authors himself, Biondi, scanning inside volcanoes with synthetic aperture. So he just published this this year. So it's good to have an independent proof of principle. So in summary, very interesting paper. It's not easy to read, but it's a major contribution if it's real. My initial impression is that the data are real. They are measuring something that's truly inside of the Great Pyramid. I think the main challenge is right now is for an independent team to go through the reasoning, through the data processing to see if they agree. Of course, this went through review and the reviewers ended up accepting the paper. So there has already been a peer review. And then the Egyptologists have to take a look and see, what they think about it. If it certainly confirms what the muon people see, but it's a much more sensitive method, obviously. I think the other main question in terms of the interpretation is, are these hotspots actual man-made voids inside? In other words, was it architecturally designed, or are these spaces that have to do with either the way that the pyramid was made? Maybe there's in some places more mortar than rock than stone. So does it have to do with the materials that were used? Does it have to do with damage to the pyramid that happened from earthquakes? I mean, theoretically, I guess you could still put all of that on the table, but I have to tell you, when you have such a regular symmetric structure, like here, this is not easy to explain with just random post-construction damage from earthquakes. And it's also not easy to explain all of this with you know, materials like, say, I mean, if you wanted to say that this was caused by more resonant material put into the pyramid in these locations than in the other locations. I mean, you know, theoretically you could make the case, but it just doesn't make sense for this to be only present in, you know, in this kind of distribution. And look at the structure that you get out of it. This is so structural. This is so non-random in terms of its shape, that it just begs the interpretation that somebody designed this on purpose. This is part of the architecture, part of the intentional design. Anyways, this is all I have for it. If you have any questions, just put them in the comment section. I'm going to put some links up, and then I will try to respond as best as I can. Remember that I am not an expert in radar technology. If I made a few mistakes, please, if anybody knows, please put them in the comment section. And so anyways, I hope that this helps you to understand this amazing paper a little bit better.